Welcome back to study room. So today we will be studying about potential energy. So let's get started. Let's do one activity to demonstrate potential energy. So you've taken a table, you've taken a box above the table, placed on the table at some height. Okay. So when raised to a greater height, it can do more work and hence possesses more energy. This implies that it has acquired some energy. The energy gets stored due to work done on the object. Okay. So it is like potential energy which gets stored due to work done on the object due to height. Okay. So notice the arrow flying off the bow. Notice the change in the shape of the bow. Have you ever seen, like, you have a bow and there is this arrow which is flying off the bow. So do you see that there is the change in the shape of the bow, right? So the potential energy stored in the bow due to change of shape is thus used in the form of kinetic energy in throwing of arrow. So basically your energies are convertible. Energies are convertible. They can be we can transfer one form of energy into another. One form of energy to another. Just like in the case of bow, we are transferring the potential energy into kinetic energy. When the arrow is thrown, it goes with some velocity, with some speed. And when your bow is stretched, you give it some distance, some height. You are storing potential energy. And when you are throwing the arrow, you are converting it into kinetic energy. Okay. Potential energy. Slinky acquires energy when stretched, right? A spring also acquires energy, right? When stretched. Okay, and it gains energy when squeezed. When you squeeze it, it gains energy. Have you ever wondered where this energy comes from? This energy is your potential energy. Okay. From the force you apply, this energy comes. Okay. So the energy transferred to an object is stored as potential energy. Which form of energy gets stored? Potential energy. Okay. And which form of energy is used in motion? Your kinetic energy. So it is stored in potential energy if it is not used to cause a change in the velocity or speed of the object. If energy causes a change in velocity or speed, then it is kinetic energy. Okay. The potential energy possessed by the object is the energy present in it by the virtue of its position or configuration. So this is your potential energy, that is at some height. It's stored energy, right? Kinetic energy has some speed, right? Kinetic energy has some speed. So potential energy of an object at a height. An object increases its energy when raised through a height. This is because work is done on it against gravity while it is being raised. The energy present in such an object is gravitational potential energy. Okay, so if an object, for example, this is an object, it is increased. So it is increased by height. Now it is placed here, right? For example, on some table maybe, okay, at some height. So this, you know that the weight of the object is mg. And it is placed at a height of h. So your work done becomes mgh. This is your potential energy. Okay. It is known as gravitational potential energy, right? Because gravity is acting on it, right? At some height, the object is placed at some height. The gravitational potential energy of an object at a point above the ground is defined as the work done in raising it from the ground to that point against gravity. So this is your gravitational potential energy. I'll ask you, define gravitational potential energy. So it is the work done in raising it from the ground to the height, right, against gravity. Expression for gravitational potential energy. The minimum force required to raise the object is equal to the weight of the object. And what is the weight of object? We know the weight of the object is m into g, right? The object gains energy equal to work done. So work done is equals to force into displacement. Force mg is applied and a displacement of height h happens. So work done is equals to F into S, force into displacement, mg into your displacement is h. So work done is mgh. This is nothing but your potential energy. Okay. Expression for gravitational potential energy. Work done on the object is equals to mgh and energy equal to mgh unit is gained by the object. So this is the potential energy of the object. Okay, potential energy is mgh. The potential energy of an object at a height depends on the ground level to the zero level. Okay. The work done by gravity depends on difference in vertical heights of the initial and final position. We know that your displacement is independent of path, right? Again revising what we studied in the motion chapter, right? It only depends on your final point and your starting point. Okay. And not the path, right? It does not depend on the path along which the object is moved, correct? So this is like if an object moves from here to here, so these 2 points will matter. No matter if we take this path or this path, even if the path is this, then also our displacement will remain the same. We only have to consider the initial point and the final point. So let's do quickly one question. Let's quickly do this. Find the energy possessed by an object of mass 10 kg when it is at a height of 6 meters above the ground. When we are talking about height, we are talking about stored energy. We are talking about potential energy, right? We will be calculating potential energy in this case. When we are talking about the motion and moving car and everything, we were talking about kinetic energy in that case. Okay. So let's quickly calculate the potential energy. We know potential energy is mgh because mg is your force and h is your displacement in case of potential energy. So let's quickly calculate. Mass is 10 kg. 10 into, if we take, g is equals to 9.8. 10 into 9.8. And what is your height? Height is your 6 meters. So what is your potential energy? 98 into 6. That is 588 joules. Okay. Let's do one more question. An object of mass 12 kg is at a certain height. Okay. We are not given the height. Okay. We are told that there is certain height. If the potential energy of the object is 480 joules, we are given potential energy is equals to 480 joules. Then find the height at which the object is with respect to the ground. With respect to the ground, okay. So your potential energy will be mgh, right? Again, 12 into, we have to take g as 10. 10 into h is equals to potential energy, that is 480 joules, which implies h is equals to 480 upon 12 into 10. That is your 4 meters. Don't forget to put the units. Okay, so it's very easy. You just have to plug in the values in this formula. Okay. So let's do one more topic today, that is energy conversion. So how do green plants produce food? Where do they get the energy from? Have you ever wondered about these? Energy can be converted or transformed into one or from the another form. Like energies can be transferred. Energies can be converted from one form to another. For example, you all have you ever done cycling? Okay. So firstly, when you're paddling, you are storing the potential energy. Then your rims of the wheel, they move, converting it into kinetic energy. So you see how this conversion occurs. Firstly, energy is stored, then kinetic energy, then energy stored, potential energy, then kinetic energy. What is the law of conservation of energy? This is very, very important. So what does this say? That energy can neither be created nor be destroyed. it can only be converted from one form to another. What does that mean? That if, for example, if you have 10 joule potential energy, for example, stored in a spring, okay, and it is changed into kinetic energy, you will not lose any energy. 10 joule, if you have 10 joule potential energy, it will be converted into 10 joule kinetic energy only. If you are, transferring energies, the total energy will remain conserved. It will remain unchanged, okay. So energy can only be converted from one form to another. It can neither be created nor be destroyed. The total energy before and after the transformation remains the same. So it will be very helpful for us to calculate the different forms of energy, because we know that total energy remains conserved. Interconversion of energy. Let an object of mass m be made to fall freely from a height h. Okay, so we are falling it freely. Under free fall, your initial velocity is 0. At the start, the potential energy is mgs. At some height, like when you're dropping, at that very point, your potential energy is mgh, right? Because it is at a height h from the ground. And kinetic energy is 0. At this point, you don't have any speed, right? So your kinetic energy is 0 at the topmost point. So when it is under free fall, at this final point, what will happen? What will happen here? You will have no height, right? You have reached the ground. Here your potential energy will become 0 and your kinetic energy will be some, like you will have some speed, right? Half mv square, your kinetic energy. So this is how your energies get converted, So your energy always remain conserved. Energy will not be lost. It will only be transformed from one form to another. Just like here chemical energy is transformed into mechanical energy. Petrol, diesel, these are chemicals. So they produce chemical energy, and this is converted into mechanical energy and your car moves. Okay, in the tree, potential energy, stored energy, kinetic energy when the apple fell, right? That is your kinetic energy. Interconversion of energy. So the total energy of the object is mgh. As it falls, its potential energy will change to kinetic energy. As I told you, right? Here potential energy is mgh and your kinetic energy is 0. In somewhere in between, you have equal potential energy and kinetic energy, right? Your mgh will be equal to half mv square. And at the bottommost point, you will have no height. Your height is 0, so your potential energy will become 0 and your kinetic energy will be maximum, half mv square, right? As the fall of the object continues, the potential energy would decrease. Yes, potential energy is decreasing as the fall continues and kinetic energy is decreasing and kinetic energy is increasing, right? Here kinetic energy is maximum and at top the potential energy is maximum. Potential energy plus kinetic energy is equals to constant. So your total energy, for example, in this case is potential energy plus kinetic energy. The sum of potential energy and kinetic energy would be same at all points. So for example, here your potential energy was maximum, kinetic energy was 0. Somewhere in between, both will be equal. Somewhere kinetic energy will be greater than potential energy. Somewhere potential energy will be greater than kinetic energy. But and at the bottommost point, your kinetic energy will be maximum. But at every instant, one thing is constant. What? Your sum. Your sum of potential energy and kinetic energy remains unchanged. So potential energy plus kinetic energy is always constant. That is, mgh plus half mv square is equals to constant. During the free fall of the object, the decrease in potential energy at any point appears as an equal amount of increase in kinetic energy. The amount by which your potential energy decreased by the same amount of kinetic energy will increase. Thus, a continual transformation of gravitational potential energy into kinetic energy. So, observation, we demonstrate the rate of work done. So, okay. For example, let's do this example. So, there are two children, okay. So, for example, there are two children, A and B, and A takes 20 seconds to do some work and B takes, suppose 50 seconds to do the same work. So we'll say that work done is same even when A takes lesser time, B takes more time than A, but if both are doing the same work, right? So work will remain same, but A has taken less time than B to do the work. So now we say about the concept of power. Power measures the speed of work done. That is how fast or slow the work is done. Power is defined as the rate of doing work or the rate of transfer of energy. Okay. So we know that one person is doing the same work in lesser time, one is doing the same work in some more larger time, right? So we define power for that very thing. Okay, it is rate of doing work or rate of transfer of energy. If an agent does a work W in time T, then power is equals to work upon time. So let's derive the unit of power. So as your power is equals to work upon time. What is your SI unit of work? Tell me. We denote work in joules, right? And what is your SI unit of time? Seconds. So your SI unit of power is joule per second. Okay. And we give it one special name, that is watt. Joule per second is equals to watt. So what is 1 watt power? It is the power of an agent which does work at the rate of 1 joule per second. So 1 joule of work is done in 1 second. Okay. Power is 1 watt when the rate of consumption is 1 joule per second. Okay. So units of power. So when we talk about power, we talk about higher units, in practical applications. For example, the power consumption in your houses, it is measured in horsepower. Okay, other units are like kilowatts. Okay, so 1 kilowatt is 1000 watts, right? 1 kilowatt is 1000 watts, that is 1000 joule per second. Average power. The power of an agent may vary with time. This means that the agent may be doing work at different rates at different intervals of time, right? Different work in different intervals of time. Suppose 10 joule work in 2 seconds and 20 joule works in suppose 10 seconds. Okay. So, average power is obtained by dividing the total energy consumed by total time taken. So, what is your average power? You sum total the total energy, all the energy which is consumed, and you divide it with the total time which is taken. Let's do one example. A boy of mass 50 kg runs up a staircase of 45 steps in 9 seconds. If the height of each step is 15 centimeter, find his power. Take G is equals to 10 meter per second. So we know that power is work done upon time taken. Firstly, we'll calculate the work done. So how much work is done? Work done is equals to mg into h, correct? Right. So let's calculate this, okay? Yeah. So he travels 45 steps in 9 seconds. Okay, and the height of each step is 15 centimeter. 15 centimeter is the height of each step. That means your height of each step is 15 by 100 centimeters, correct? So, what will be your h? H will be, you have 45 steps. Okay, so, and height of each step is 15 by 100 meters, right? 45 into 15 by 100 will be your h. Okay, so what will be your work done? Work done will be, what is your mass? Mass is your 50 kgs. 50 into 10 into, what is your h? 45 steps, and each step is 15 centimeter long. So your height will be 45 into 15 by 100. Okay, so this will be your what? mgh upon time taken. Okay, this is your work done. And what is your power? It is your work done upon time taken. So it will be how much? How much work is done? It is 500 into 6.75 upon how much time is taken? 9 seconds. So your work done, your power comes out to be 375. Okay, 375 watt. This is your power. Okay, or we can also say 375 joule per second. Okay. Let's do one more question. Two girls, each of weight 400 Newton, climb up a rope through a height of 8 meters. Okay. Girl A takes 20 seconds while girl B takes 50 seconds to accomplish this task. What is the power expended by each girl? Okay. So here for girl A also and girl B also, we'll do one partition and we'll calculate for both. So firstly, let's calculate for girl A. So what is the weight of the girl A? It is 400 Newtons. Okay, they climb and she climbs a rope of height 8 meters. Okay, in 20 seconds. So this is for girl A. So let's calculate the power. What is power? Power is nothing but work done upon time. Okay. So your force is nothing but M into G. Correct. So you have mgh. Your work done. Work done is 400 into 8. That is your 3200 joules upon what is your time? Time is at 20 seconds. Okay. So for girl A, power is 3200 joules upon 20 seconds. She takes 20 seconds to do the work. So power comes out to be 160 watt, or we can say 160 joule per second. Okay. So now let's calculate for girl B. So your force is how much for girl B? Both are of weight 400 Newton. Force is 400 Newton. That is your mg, right? And she travels at a height of, she also travels at a height of 8 meters. Okay, h is 8. And she takes 50 seconds. Now your time taken is more, 50 seconds. Okay, what is your power? Power is mgh upon time taken. What is your 400 into 8 upon 50? That is your 64 watt. So you see here the power for girl B is 64 watt and for girl A is how much? 160 watt. So since she takes more time, so less power. She takes lesser time, so more power is expended. Okay. Okay. What is power? We have already defined this. Define 1 watt of power. You all can do this, right? A lamp consumes 1000 joules of electrical energy in 10 seconds. Okay. So your energy is 1000 joules. Electrical energy in 10 seconds. 10 seconds. What is its power? We know power is equals to energy consumed upon time taken, right? So we'll quickly calculate this. What is the energy consumed? 1000 joules. Time taken 10 seconds. How much is the power? 100 joule per second, or we can say 100 watt. Okay. Next question, define average power. What is average power? We already defined it. It is total energy consumed. Average power, we have, don't forget it is total energy. You have to sum all the energies, right? Total energy consumed upon total time taken. Okay. So some commercial units of energy. Bigger unit of energy called kilowatt hour is used to measure. So one more energy unit which I would like to tell you is 1 horsepower. It is of very much commercial importance. Okay. Okay, and in 1 horsepower there are 746 watts. Okay. So 1 horsepower is equals to 746 watts. It's very important for exam point of view also, and it is used in daily applications. So horsepower is a unit of power like which is majorly used because 1 horsepower is 746 watts. It is used in commercial purposes. So you know about kilowatt hour, right? 1000 joules of energy every second, 1 kilowatt hour, right? So 1 kilowatt hour is 3.6 into 10 to the power 6 joules. Let's do this conversion. So 1 kilowatt hour. Okay, 1 kilowatt is equals to 1000 watt. And 1 hour is equals to 3600 seconds. Okay, so 1 kilowatt hour. This energy, how much is this? 1000 into 3600. That is your 3.6 into 10 to the power 6 joules. Okay. So the energy used in households, industries and commercial establishments are usually expressed in kilowatt hour. Electrical energy used during a month is expressed in terms of units. Let's do this question. An electric bulb of 60 watt is used for 6 hours per day. Your power is 60 watt. It is used for 6 hours per day. Calculate the units of energy consumed in 1 day by the bulb. So let's calculate. Okay. So your power will be 0.06 kilowatt, right? Okay. So we know that power is equals to energy consumed upon time taken, right? So what will be your energy consumed? It will be power into time, right? Energy consumed will be power into time is equals to 0.06 kilowatt into time, 6 hours per day, right? So how much power is consumed? 0.36 kilowatt hour, okay? Okay, so it is 0.06 kilowatt hour, or we can say 0.36 units. So let's do a quick revision. Work done on an object is defined as the magnitude of the force multiplied by the displacement of the object. We know work done is equals to F dot S, right? The unit of work is joule. Work done, we express it in joules. And 1 joule work is when 1 Newton of work is done in 1 meter, right? Work done on an object by a force would be 0 if the displacement of an object is 0. Okay. An object in motion possesses what is known as kinetic energy of the object. We talked about this, right? Half mv square. If an object has some motion, some velocity, half mv square, right? The energy possessed by an object due to its change in position or shape is called potential energy. So if we talk about spring, what kind of energy is stored in spring? Potential energy, right? The gravitational potential energy of an object of mass m raised through a height h from the earth is equals to mgh, right? This is your potential energy. And what is your kinetic energy? If work done is in the form of kinetic energy, then half mv square, right? And what is power? Power is defined as the rate of doing work. So power is equals to work upon time, right? What is SI unit of power? Watt. 1 joule per second. The energy used in 1 hour at the rate of 1 kilowatt is called 1 kilowatt hour, right? What is 1 kilowatt hour? We just discussed this. Thank you so much, and we are at the end of this chapter. Do revise, do ask questions, and if you have any doubts, just feel free to ask. I wish you all the very best, and bye bye. See you soon.